Okay, well, we're back here for the second part of our lecture, second video on this lecture on properties of slope. In the first part we talked about defining slope and numerical computation of slope and graphical interpretation of slope. We talked about its connection to steepness, about parallel and perpendicular lines, and vertical and horizontal lines. Hello, we're back. This is part 3 of this video, part 3 of our lecture series on properties of slope. Today we're going to talk about something called the difference quotient and a symmetric difference quotient and some applications. So here's an application I want to look at. The following table gives the position, say the mile marker, and time in hours after noon for an automobile going down the interstate. So at time 0 they're at mile marker 10, at time 1 they're at 1 hour later they're at mile marker 60, and so forth. So we want to compute some average speeds for this vehicle. Okay, first of all, what would the units be of the average speed? Well, the units of time are hours, the units of position are miles. So the average rate of speed, average rate of change, is the slope. So that's going to be a delta P divided by delta T. So it's going to be P units divided by T units, output units divided by input units. So that is going to be miles per hour, and that's our speed. That makes sense in this case. So go ahead and figure out these different slopes or average rates of speed and come back when you're finished with those. Press pause now. Well, in each case, look, we're finding a delta P divided by delta T. So from 1 o'clock to 4 o'clock, we're using the point 160 and 264 and finding a slope. So delta P or delta Y is 264 minus 60, which is a distance traveled of 204 miles. And the time, delta T, is 4 minus 1 is 3 hours. So we went 204 miles in those 3 hours. That divides out to be 68 miles per hour. So from 1 o'clock to 4 o'clock, the car is averaging 68 miles per hour. Now what about from 1 o'clock to 3 o'clock? Well, this time we're using the point 160 and the point 190 and finding the slope. So delta Y or delta P is 190 minus 60, so that's 130 miles, but delta T is 3 minus 1, so that's 2 hours. So in that 2-hour time period, the car traveled 130 miles, so that averages out at 65 miles per hour. What about from 1 o'clock to 2 o'clock? Okay, that is 120 minus 60 is 60 miles. 2 minus 1 is 1. So in that 1 hour period they went 60 miles, so that is 60 miles per hour. Now within that hour they could have gone up or down a little bit, but it averaged out to be 60 miles an hour. Now let's just take in those three things. Which one is the better estimate for how fast it's going, say right at, say right at 1 o'clock? Well, it's going to be closer if we can take the interval closer. So from 1 to 4 is sort of too far away. It's a 3-hour interval. From 1 to 3 is a closer interval, so that's going to be a better estimate. 1 to 2 a better estimate still. We could do better and better estimates by getting closer and closer. Unfortunately, 1 hour increment is the smallest we can make it in this particular table. But if we had a table with more information in it, if we checked our position more than once an hour, perhaps we could get a better estimate of our speed at a more, at a particular time. So what's the average from 2 to 3? Well, that's 190 minus 120 is 70 miles, and that's 3 minus 2 is 1 hour. So 70 miles per hour is the average speed there. Now, which one of those would be the best estimate for say right at 2 o'clock? Okay, well, if you think about it, on the one hand, a smaller interval would be better. Okay, so for example, going from say 2 to 4 wouldn't be as good as from 2 to 3. But there's no reason why 1 to 2 would be any better or worse than from, say, 2 to 3. So you'd think the slope 3 from 1 to 2 would be about as good an estimate as from 2 to 3. So you might get a better estimate by just averaging those two. So if you take 60 plus 70, divide by 2, you get 65 miles per hour. Well, if you notice, that turns out to be the same thing as just taking the 1 o'clock and 3 o'clock points and the slope there. And so that turns out to be the same thing. So slope 2 is the average of slope 3 and slope 4. And that, either way you do that, by either finding the slope 3 and slope 4 and averaging them, or better yet, the easier way, just finding the slope 2 from 1 to 3, that's going to be 65 miles per hour. It's our best estimate. We get a better estimate if we would narrow the interval. So if we sort of formalize this a little bit and put some symbols in here, what we're talking about here is finding some slopes or average rates of change from a table or from a graph or a formula. And let's say we have our formula f of x. Then we could talk about a specific x, let's call it a, and then the y that goes with that would be the specific y, f of a. So we have the point a, f of a, which is sort of in the middle of our table right here. Now what we could do is move over a little bit, say, in this case if it's time, a little bit into the future by adding h to a. Or on the graph we're going a little bit to the right, let's say. And so this gives us a new x value, which we'll call a plus h. We want to think of h as maybe being something kind of small. Wouldn't have to be anything small, but in the context we want to use it here, we want to think of h as being small. So we go over some small amount h, and that gives us a new point, a plus h. And of course then the y that goes with that will be f of a plus h. Notice, by the way, that f of a plus h is not f of a plus h. It's not f of a plus f of h. It is something different. Okay. And likewise, we could go a little bit to the left on our graph, or a little bit earlier in time, by doing subtract this h from a to get a new x value of a minus h, a little bit less than a, and then find its y value, which would be f of a minus h. Again, f of a minus h is not f of a minus f of h. It is not f of a minus h. It's something else. So you take a minus h and then evaluate it at that point. Now, if we take the slope and we say we take these last 2 points, a f of a and a plus h, f of a plus h, and do that slope, that's known as a difference quotient. Work out what the formula would be with these symbols for the slope there. Go ahead and write that down, and when you're done, come back. Press pause now. Well, this is called the difference quotient. You take the delta y is f of a plus h minus f of a, and then delta x is a plus h minus a, which reduces to just h. So in the difference quotient, this h is delta x. Okay, so in other words, to say that is delta x on the bottom, and the top is f of a plus delta x minus f of a, because h is delta x. And this is called a difference quotient because it is a quotient of differences. Remember, a fraction or division, the answer to that is a quotient, called a quotient. So we have a division, so it's a quotient. And the top and bottom are actually differences. The bottom is delta x and the top is delta y. Difference in y's and difference in x's. So we have a difference quotient. So this is just a formulaic way of basically writing a slope where we start at the point a, f of a, and we move to the right a little bit to some point a plus h, f of a plus h. Now what if we go from a minus h to a plus h, in other words, from this point here, a minus h, comma, f of a minus h, all the way over here to a plus h, f of a plus h. That would be like, let's back up. So the difference quotient, for example, would be like M4, where we took the point 2, 120, and the point 3, 190, and did the slope. The symmetric difference quotient would be more like M2 here, where we were interested in what's happening at 2, but instead we take stuff before and after it to find the slope. Okay, so what would the formula be there? That's called the symmetric difference quotient. Work that out and then come back when you got it done. Okay, so the symmetric difference quotient is f of a plus h minus f of a minus x minus a. No, that's a minus h. That's wrong. Okay. In fact, let me just fix that now. This should be a minus h. But notice that I don't need this. Okay, there we go. So notice what I'm doing is just taking this last point and the first point and doing the slope. Notice that the slope, the delta y is f of a plus h minus f of a minus h. And delta x is a plus h minus a minus h. When you distribute the negative and combine like terms, the a's cancel out, and you end up with a distance of 2h. It's a distance from h from here to here, and from here to here it's h, so from here to here it's 2h. So delta x is 2h this time, and delta y is f of a plus h minus f of a minus h. So it's a quotient of differences, but since the point we're interested in is the middle and we're not really using it, but going either side equal distant horizontally, not necessarily equal distant vertically, but equal distance horizontally, it's called a symmetric difference quotient, because the horizontal difference is symmetrically centered on our point a, f of a. Okay, so here's an illustration of this here, and this is from a Geogebra investigation that I'm going to open up that is that we can use here. Let's see. Should open it up. And when you open it, I'll post this to our site as well, our Blackboard site, so that you can get into this. Hopefully this is going to load up. So there's at the top there's some directions, and at the bottom there's a kind of a question to ask. But in the middle we should have our Geogebra investigation pull up in just a minute. It should end up looking like this particular setup here. Okay, so here we go. So here we're interested in a function, and we can change the name of the function, the formula, by typing it in here. It's f of x equals, we can type the formula in here. Right now I have x squared. If I want to, I can change that to x to the power 3, and now the graph changes. I want to go ahead and use x squared, so I'm going to change it back. But you can change that. You can also change the value of h and the value of a. So if I've changed a to 3, notice it moves the point here, a f of a, to 3, 9. I want to center it at 2, so I'm going to go back to 2 here. And so now we're at this point right here, which is a f of a is 2, 4. Because you plug in 2, square it, you get 4. So 2, 4 is our point. You can see the ordered pair down here. Here it is sort of in table form. Here it is as an ordered pair. And so this is the point we're interested at. Now we want to find the difference quotient first, where the h is, well, I've used 1. And so this is the difference quotient you can see right here. And you can see it visually illustrated. We're going to the right h, and then we're going up, well, f of a plus h minus f of a. So what we're doing is we're using these 2 points right here in the table, 2, 4, and 3, 9. That is a comma f of a and a plus h comma f of a plus h. So this is a plus h, f of a plus h right here. This is a f of a, and we're finding the slope of this line segment between them, those 2 points, or in other words, the slope between those 2 points. So it's vertical change divided by horizontal change. So the vertical change here, 1, 2, 3, 4, 5, and then the horizontal change is 1, 5 divided by 1. That means this is a slope of 5. We can also do the difference quotient with a negative h. In this case, we can use the same formula, f of a minus h minus f of a, but we're dividing by delta x, which is minus h, so we're going down and to the left. So we're going, so delta y is negative 3, delta x is negative 1, excuse me. Divide, you get positive 3, so we have a slope of 3 here. That's a difference quotient. A symmetric difference quotient does not use the point here. Let's go back. a difference quotient, whether you're going to the right or to the left, uses the point you're kind of interested in. Symmetric difference quotient doesn't use the point we're interested in. It takes it and goes h to the right and h to the left. So for a total delta x of 2h from this point and this point. And so we have a delta y of f of x plus h minus f of x minus h, where x is a, our particular x value. And so we have our setup here, and we're dividing by 2 h's. So what we're doing is just using this point 3,9, this is the one up here, and the point 1,1, the one down here, and finding the slope of this blue line segment. Now that turns out to be, in this case 4, it always turns out to be the average of the other two. So if we show the other two slopes that run on top of each other here, let's move this one up here. They're 5 and 3. When you average them, you get 4. It always turns out that the symmetric difference quotient is the average of the two difference quotients with the same h, the h and the minus h, and work those out. Now, of course, what we want to do, the question that's asked is what happens if we change h? Suppose we get h to be smaller by half. It's starting to be harder to tell these three line segments apart. The line segments are getting closer to each other, and notice that the slopes got closer together too. So when it was 1, the slopes were 5, 3, 4, and 5. If we do a half, now the slopes are 3.5, 4, and 5, and 4.5, so they're closer together. And so what we want to think about, oftentimes the context we're going to end up doing this in is when we have a really small delta x, a really small h. Okay, and if you notice, these things are getting really close to each other. In fact, in this particular one, because I picked a quadratic, the symmetric difference quotient's not changing. Okay. If I pick a different function, like let's go x cubed, x to the 5th, let's say. Some of these are really too big to see right where we are. So let's change a to be 1. And now let's pull this down a little bit smaller. Now we can see them. There's quite a bit of difference in these. Let's see, we get the one on the top, h is where we go to the right, is 13.19, to the left is 1.94, average the two, or the slope of the blue segment, is 7.56. So these segments here are called secant segments. So the slope of those secant segments are the slope between the 2 points. If we bring this in smaller still, now these are starting to, now notice even the blue one's changing this time, but they're getting closer to each other, and it looks like they're getting really close to, looks like they're all getting really close to 5. Okay, I'm going to reset this back like I had it to begin with. Okay, let's go back to our slideshow. So here's for your notes, you'll have a static picture of one of this shows the two difference quotients, the one with the h and the minus h, where the h was 1, and then you also have negative 1 there for the delta x. And then here's where we have 2 h's going across either side for the symmetric difference quotient worked out. Now, let's see if we can do this. See if you can do this maybe without the software. Just do it by hand for f of x equals 3x squared minus 2. And see if you can figure this out for h is 0.5 and a is 2. And you can use a calculator on this. In fact, I expect you to do that. And find the difference. First of all, fill out all the points in the table. And once you have that, use that to help you figure out the difference quotient for h equals 0.5. And then the second one's supposed to say the symmetric difference quotient. Difference quotient and symmetric difference quotient. So go ahead and figure that out now. And here it is. The difference quotient Okay, first of all, let's figure out the table. Some of this I can do in my head pretty easily. A is 2. 2 squared is 4 times 3 is 12 minus 2 is 10, so that's 210. The rest of this I did on my calculator. I did 3 times 2.5. Well, I could do these in my head. Add a 0.5, got 2.5, subtract 0.5 is 1.5. And to save time, I did it on the calculator. 3 times 1.5 squared minus 2 is 4.75. 3 times 2.5 squared minus 2 is 16.75. So now I have my points. To do my difference quotient for the h's 0.5, I'm using these 2 points right here. So I'm using 210 and 2.5, 16.75. So 16.75 minus 10 over 2.5 minus 2, or just 0.5, because we don't know that's h. And that turns out to be 13.5. The symmetric difference quotient, I'm using this point and this point. Notice delta x is 2.5 minus 1.5, which is 1, which is twice h. 2 times 0.5 is 1. So we're dividing by 1 in the bottom. In the top, we get 16.75 minus 4.75, which is just 12. And divide by 1, we get 12. So that's the symmetric difference quotient. That should have the word symmetric in there. Alright, now this one's a little more challenging here. We're given a formula, f of x equals 3x squared minus 2. This time I want to put in an arbitrary a and an arbitrary h and do a difference quotient formula in general and see if we can simplify that. Okay, so use the defining rule for a difference quotient. Evaluate at these values of a and h, and then once you get done and simplify, it'll be a formula that has a and h in it, some numbers, and then use that formula to figure out the difference quotient for these particular numbers here. Okay, try this and then come back. Okay, did you get this? Remember, a difference quotient is f of a plus h minus f of a over h. So in the bottom we have h. In the top we have two things subtracted, so put parentheses. In the parentheses on the right, where we have f of a, we just take where there's an x, put an a. So that's 3 times a squared minus 2, or 3a squared minus 2. In the left, however, we want to take where the x is, put a plus h. Don't put an a and then put an plus h at the end. Put x or a plus h in place of x. So that's 3 parentheses where the x was. In that parentheses put a plus h, then it's squared minus 2. Now we just work this out. A plus h squared, you can use FOIL if you know that anagram, or the distributive property to multiply this out. And you get a squared plus h squared, but don't forget you also get 2ah. Distribute the 3, that gives you 3a squared plus 6ah plus 3h squared minus 2. Distribute the negative 1, that's minus 3a squared plus 2. Now it's getting kind of long, but it's going to start cleaning up here a little bit, because the minus 2 and the plus 2 cancel each other out, and the 3a squared and the minus 3a squared also cancel each other out. So now the numerator only has 6ah plus 3h squared. And then, as often happens with these things, you can factor an h out of the numerator and cancel it with the h in the denominator. And I've used the distributive property to pull the h out and cancel those h's, the one out front and the one at the bottom, and so the answer is 6a plus 3h. So now we have a very simple formula where I can pick whatever a I want and whatever h I want. So for example, 6a plus 3h. Let's back up to this one. If a is 2 and h is 0.5, 6a plus 3h. So 6 times 2 is 12. Okay? And then h is 0.5. 3 times 0.5 is 1.5. 12 plus 1.5 is, sure enough, the 13.5 that we found here. So if we want to do it for a equals 3 and h equals 0.1, we just plug in 3 and 0.1 here. 6 times 3 is 18. 3 times 0.1 is 0.3, so that's 18.3. Plug in a is 5 and h is 0.01. That's 6 times 5 is 30. 3 times 0.01 is 0.03, so that's 30.03. 30 and 300ths. And so if you had a bunch of these to work out, it's useful to manipulate the formula like this a little bit. So it's a little practice manipulating formulas. Notice that we're basically doing like a composition, so we've got an a plus h that we put in place of the of the x. Be careful that that a plus h goes in place of the whole x there. Okay? Multiply, square, distribute, combine like terms, some simplification happen, factor an h out, cancel the h's, and we have our simplified version. So when interpreting the slope in the context of a real-world situation, remember that it is the average rate of change between 2 points of the function, whether that's from a graph, a table, or the formula. It's also the amount that the output goes up when the input is increased by 1, assuming that the function is linear between the 2 points used to compute the slope. Or, another way to say it, even if it's not linear, it would say, okay, well, if it went up by that amount each time the x went up by 1, and you did it all out, it would still get you to the same place at the end. It sort of gives you a straight line path to get there, even though the graph may have taken a different path. The numerator of the slope is delta y, so it has the same units as the y, or the output. The denominator is the slope is delta x, so it has the same units as x, or the input. So there's always units to the slope, and they're always fractional form units. They're always output units over input units. And that can help you understand what the slope means in context. So one more example here. Let's see if you can work this out yourself. I've got 3 different real-world contexts. I'd like you to interpret what the meaning of the slope is between the 2 points from an indicative function, and I'm actually giving you a value for the slope. So I want you to interpret that slope in the context of the scenario that's there, the real-world scenario, and also be sure to include units as you're working through your problem there. So the first one, well, you can read these. Read these and come back and with an answer in a minute. Alright, the first one, the input is the day in hours since midnight, and the output's the temperature in degrees Celsius. M is -4 over an interval. So it's the average rate of change is a decrease of 4 degrees Celsius per hour. So the temperature dropped exactly. So if the temperature dropped exactly 4 degrees every hour, of course it would be linear, and then the beginning and end temperatures would agree with the actual temperatures. In actuality, this may be just averaged out, but it averages 4 degrees per hour, Celsius per hour. The output's the cost of manufacturing an item in dollars, and the input is the number of items manufactured. If the M is 12.5 on an interval, so the average rate of change is, it's cost over item, so it's dollars per item. So that's $12.50 per item. This is what's called the marginal cost, or the additional cost of making one additional item. On top of making all the ones before, this is the additional cost for one more item. The input is the year and the output is your salary. M is $250 over an interval. That says your average rate of change is an increase of $250 per year. So you're an average of $250 a year for your raise each year. So what should you be able to do after watching this series of 3 videos? You should be able to find the slope between 2 points of a relation, identify linear relations that do not have a slope or that have a slope of 0, in other words, vertical and horizontal lines. Understand the relationship between slope and parallel and perpendicular lines. Interpret the meaning of the slope graphically, numerically, and in context. Determine the characteristics of the direction and concavity of a graph based on looking at the slopes between successive points of the function. Identify and classify extrema and inflection points from a graph. Calculate a difference quotient and symmetric difference quotient at a point, and get a general formula for a difference quotient or symmetric difference quotient at an arbitrary point.